Hey everybody, this is Larry. This is me over Q4 of the weekly contest 497. Good subsequent queries. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. I think this one was obviously hard. I didn't solve it, but I was only missing one small piece at the end. I mean, maybe it's a big piece because when you miss a piece, it doesn't matter if it's big or small. But first thing I would say is that this video, of course, is to walk you through my thought process more than just the solution. Look, you can read the solution from a lot of places, right? My point is just to kind of go through my thought process and how I solve this, right? Yeah. So the first thing to notice, of course, is that subsequence, right? Meaning that we don't care about the order, we only care about the numbers. And of course, we have queries. It took me a little bit of time, and of course, also n is 50,000 or whatever. But each prime is pretty small as well, or each number is pretty small, sorry, and p is also small. And then you have this GCD of each element is exactly p. So it actually took me a little bit of time to understand what it means by looking at all the, and you'll see this during the live portion if you want to watch it on like 2x or 5x or whatever, is that it took me a little bit of time to understand what this means. And what this does mean is that, well, you could separate each of these queries, right, into two buckets, right? One is, oh sorry, not queries, but each number into two buckets, right? One is numbers that divide p, or p divides them, and then the other is numbers that p don't divide them. And of course, if p does not divide those numbers, then the GCD cannot be p if it contains that number, so we just kind of exclude them, right? So now we only care about numbers that divides p, right? Or p divides those numbers, right? For example, if p is even, we don't care about the odd numbers because the odd numbers will never give you a GCD that is an even number, right? If p is 2. So that's kind of the idea. And then the next observation is just that, well, what if now you have all the numbers that divide p? Well, what happens? Well, what happens is that now we're trying to get, now if we divide every of these numbers by p, then now our problem becomes trying to get a GCD of a subset of those numbers to be 1, right? Well, or subsequence, okay, subsequence of those numbers to be 1, right? Meaning that, okay, let's actually, I think this is big enough for to explain, right? Or to visualize a little bit. So you have these numbers, and then now what happens is that, let's say these are all even, so then we pre-process to be 2, 4, 6, 8, right? So because we divide each of these numbers by 2. So now we're trying to find all these numbers in which, or we're trying to find the GCD of subsequence of them such that it equals to 1. So then, for example, if we convert one of these numbers to, I don't know, this one is 6, then now this is going to be 3 because we divided by 2. And then now, well, there's an easy subsequence of just 2 and 3. 2 and 3 have a GCD of 1 is my point, and that gives you a yes answer, right? That's the only difference. Another observation, of course, is that GCD, because now we're trying to get the GCD to 1, right, of some subsequence of this. Well, what can we do? Well, GCD is kind of, because we're trying to get it to 1, it is additive in that way. And what I mean by that is that when you add more numbers to like, let's say you have 2 and 4, the GCD is 2. If we add 3, then now it's going to be 1. Well, we add an 8, well, it doesn't change anything, it's still 1, right? So the GCD will only go down toward 1 as you add more numbers, which lends itself to a greedy solution, right? Meaning the greedy solution being use all the numbers, right? All the numbers that are divisible by p, right? Hopefully that makes sense because we already established that part, but I want to reiterate it just so that it doesn't sound like I'm missing something, right? Because p is even, we could get all these numbers. And that's basically the idea, right? That's the core idea that allowed me to start building. And then now what happens? Well, now, let's say if this was static, we're done, right? kind of. We'll talk about the kind of later. But now we have queries. What does the queries do? Well, we update them. And update them. Now we're just trying to figure out how to because we have to do updates. Then now we have to try to get the GCD part in a very fast way, because we cannot just keep on, especially if like n is equal to I don't know, something big. If n is equal to, or not n, sorry, actually with n, if n is like 10,000, then you're going to run a 10,000 loop to get GCD to 1, right? So that's not going to be acceptable. So especially now that we have updates, right? We have q is equal also 10,000. I think it's actually 50,000, but let's just, 10,000 is already big enough, right? So we have updates, and update is pretty simple, kind of, right? Because you can decompose them into removal and add, right? Add is easy in quotes, because to keep a running GCD just needs more GCD, right? Because GCD, what's it called? Distributive, right? Because GCD of this case, that means that you have GCD of all the numbers. So if you're adding a new number, it's just one more GCD. Turns out this is not relevant, but that's my thought process as I was writing it, right? But now removal is tougher because you can't just remove a thing. So then I had to export this part. And what I found is that, well, remember, for this problem, we do not need to care about the GCD per se. We only care whether it is a binary question of whether GCD is 1. Right? Then now what? Well, what makes a GCD is 1? Well, again, we refer back to greedy. Then now, what does that mean? If we use all the numbers, that means that if one number does not share a prime divisor, then the GCD is 1, right? And what do I mean by that? I mean, this is very specific, but what I mean is, okay, let's break it down, right? And this, I'm saying it and it sounds easy and it's like, oh, obvious. Even if you get it, if you understand it, you'll be like, oh, it's obvious. But if you watch the live portion, it took me a little bit of time to even just break it down, right? Because for example, 2 is equal to 2, 4 is equal to 2. Let's go back to, what was it? 12 for a second, right? So it's going to be 2 times 2 times 3, right? So 2 times 3. Yeah. And then what's it, 16 is 2 to the 4th, right? So all these, of course, what happens? Well, all these shares are 2, right? As the prime divisor. But if there is a prime, and this is, we have 6, or it was 6, and then which we convert to a 3. If this is 3, that means that now there's a prime, there exists, or rather the most common prime, if the most common prime is not used by, or if there does not exist a prime in which all the numbers are divisible, then the prime is 1. Maybe that's better, right? Because I think I'm mixing things up. And what I mean by that is that, okay, well, and when this was, I forget what it was. What was it? Okay, when this was 6, it's 2 times 3. Well, all these shares are prime, right, of 2. And we don't actually, for the purpose of this problem, we actually don't care that this is 2 to the second, because again, because all we care about is whether the GCD is 1, right? So 2 to the second power doesn't matter. why doesn't it matter? Because it doesn't matter whether the GCD is 2 or 4 or 8 or other powers of 2. We just care whether it's 1 or not. So therefore, we can actually reduce this a little bit, right? And here we can see that all 4 numbers has a 2. And that means that the GCD is going to be at least a 2. It could be 4, it could be 8, it could be other powers of 2s, it could be other numbers. If we have, like for example, if they're all 3s or 6s, like it doesn't matter, right? Then the GCD will be 6. But we don't care. We only care that the GCD is not 1, because all the numbers, if you divide all the numbers, the greatest common divisor is going to be 2, right? But if you remove one of these, then now, well, there exists one number in which it doesn't contain a 2, and because it doesn't contain a 2, that means that the 2 doesn't matter anymore, right? And therefore that the GCD is going to be 1. And that's the idea, is that and another way to write this, and this is a reduction, an observation that took me a bit of time. So I'm saying this, like I said, it sounds obvious when you're sitting down and understanding it, but that's why, and it maybe not even if I'm explaining it poorly, but if you watch the live portion, maybe you'll see how I work it out. But it means that the most common prime is not used by all the numbers, right? And the reason why I rephrase it is because this query now means that all we have to do we pre-process each number, or maybe not you pre-process as well, to process each number to its prime components, and then count the number of primes being used by each number, right? Oh, sorry. No, count the number of numbers used by each prime, right? So, for example, in this case, maybe you would store like you just have a frequency table. F of 2, we have 3 2s. F of 3, we have 1 3, right? And then now we can see that, well, there's a 4. There are 4 numbers, so this is no good. But we had this as a 6. It's 2 times 3. This is 6. Oh, sorry, this is 4. My bad. And this means that the GCD is not 1, right? So okay, so that's basically the idea. There are more like data structure-y stuff here, right? Because for this, to make it fast, I actually use a sorted. So you have the prime decompose. So that's why this problem is so tricky, right? Because there's all these components. But that's why I want to explain this in the way that I did, or I am doing it, because that's how I jump from one step to another. You may jump from other steps as well, obviously, if you explore this problem. But this is just showing me. I'm just showing you how I break it down in ways to kind of solve this problem, right? Not just to explain the solution, but explain how I solve it, so that maybe you see, like I have this problem, I want to go this problem, and I have to pre-process each one, and then now, wait, so, and then that step, actually this is like the same thing, right? But step 2 is figure out how to get the most common prime in a fast way. It turns out that it's not actually too bad, because you don't have that many primes, but you still have to do it, right? And then now this part, so one is that we have these frequency tables to just keep track of the prime components and how often they appear. But then now we keep a sorted list of the frequency, so that we can refer to the most common piece in O of, I think it's O of 1, because or O of log n. I don't know if it's and this is not log n, this is log p for the number of primes. I say maybe O of 1 because I don't remember if sort list cache is the biggest entry or not. Could be wrong. Either way though, either way it's gonna be fast enough, so that's why I never looked it up. Maybe I should one of these days. But yeah. So as you can see, I keep on breaking it down into different problems that I know how to solve, right? So hopefully, this is why I kind of break it down this way. And then now, so that's basically it. This is 90% of the problem. But as they say, 90% of the problem is, you spend most of it, you spend 90% of the time on the first 90%, and you spend 90% of the time on the second 90%, right? And that's what happened here. So this is the way that I did it, by the way, with the prime factorization and stuff like this. I also want to point out that I did notice other solutions. You can also use GCD segment tree, right? So that allows you to get the GCD of all the components in a very quick way, right? So there are different ways of doing it, but this is the way that I did it, so this is the way that I'm explaining it. Hopefully, with this hint alone, this just replaces the question of we only care if the GCD is 1, right? So yeah, this answers that question. So that's all I'm going to say about this one. I'm not going to go over how to solve it with GCD segment tree. I mean, if you're going that far, then you could do it anyway. Okay. So the other 90% of the part, and of course now we have to change. Okay. Oh yeah, removal, right? So now removal. I mean, this is basically what we had to do, right? And now that we have this setup, removal is just bookkeeping, right? It's not easy bookkeeping, but it's bookkeeping because we just have to change the frequency table when we when we remove a number, we change the frequency table. We also change the sorted list of the frequency. That's basically the idea. That's basically it. And add now, well, we cross this out, and it's just as easy, kind of. I mean, it's easy if we already did the removal because it's the same, right? It's just process each number to its prime component, and then update frequency table, update sorted list of frequency, right? I mean, pretty I mean, once you got the other part, all this is just bookkeeping, right? Hopefully that isn't too bad. Okay, so now that we got this done, we're 90% done, and this is where I ultimately end up with about like half an hour, 40 minutes ago, something like that. But I missed a piece, and that piece I just couldn't figure out until afterwards. I got a hint, and it is that its length is strictly less than n. So it turns out that when I don't know, I don't know if I missed this strictly, but I didn't value it enough. Like maybe I did read it correctly, but I just was dismissed. So I thought, oh, it's just a small detail. But it turns out that it was the small detail that sunk my ship, if you will. And the idea now is that, well, listen, if the number of primes, or not number of primes, I call it prime because they use p, it's confusing. But if the number of relevant things, like after we divide it by 2, if all the in my code I call it good, but if the number of good elements is not n, then we're done because by definition we're strictly less than n anyway. But what if with all the numbers are n? All n of the numbers are divisible by p. Then what happens? Well, the thing is that then now the greedy part doesn't hold. We can no longer use all the numbers because we cannot use all the numbers, right? I mean, sounds pretty straightforward, hopefully, because that's just literally you cannot do it, and it's just a problem statement, right? So then a lot of this kind of breaks down, right? And it turns out that like you cannot do like I tried like many different hacks and I couldn't get it to work with like -1, make assumptions here and there. But it turns out that you can have like, for example, you can have, I mean, I don't have the numbers on me, but you can have a prime such that, maybe P1 is used by index 0, 1, and 2. P2 is used by index 1, 2, 3. P3 is used by index 0, 1, 3. P4 is used by index 0, 2, 3, right? Something like that. But basically, the thing is that all of these, right, uses 3 elements, right? But so if you use all 4 primes, or if you use all 4 numbers, the GCD is 1 because no prime is common to all numbers. But but you have to remove 1, and removing 1 will make the GCD not 1, right? And you could prove it to yourself, right? For example, if you remove the index 0, right, then now you have this number, right? And this number, the GCD of this is just P2, right? Whatever it is, because you only have 3 elements left after removing 1 element, and the GCD is by definition P2, or multiples of P2 or whatever. You get the idea, right? But not 1 anyway. So okay, so this, honestly, it took me an hour. I couldn't figure it out. I had to take a hint. And the idea here is that, well, there are two cases, right? One is if we have more than you could do the math more precisely, but if n is greater than equal to, say, 20, right, then it is always true that you can find a GCD is equal to 1. So this observation I wasn't able to make, and the proof behind this is just actually your classic pigeonhole principle, right? Because if you have 20 numbers, each of those numbers, because it only goes up to 50,000 or whatever, has at most, I think I did the math and it's like actually only 10 primes, but let's just say at most 15 primes, right? I mean, we're hand waving, but the numbers are small enough that it doesn't matter, so I'm just saying it is, right? At most 15 primes, right? So yeah. So if you have, I mean, and pigeonhole is even more tighter than this, but if you have 20 numbers and 15 primes, then there will exist, and remember, these are not 15 distinct primes, right? Each number has 15 primes, but and the reason why I say, oh, let me prove this for a second, right? So the reason is that it has 15 distinct primes, right? So for example, number 1 could have 2 times 3 times 5 times 7 times 11 times 13 ... right? And this may already be close, right? I mean, I say 15 because I'm just too lazy to look it up. I think it's actually like 6, actually, because I think I did look it up. But yeah, so it could, this could be number 1, right? So array element 1, and A2, if you want, it's either that it has the same yeah, it's either that, oops, how did that copy and paste go? Yeah, it's either that as the same, right? And such, right? So that's kind of the idea, right? Is that actually, now I forgot a little bit. But yeah, but that's basically the pigeonhole principle, right? Is that oh yeah, I think I missed a condition. That's why I didn't talk about it, which is that yeah, okay, yeah. The other condition that I forgot to mention. That's my fault. I got a little bit confused. this is a very long video, and so that happens. Keep in mind that no prime is common to all numbers, right? Because if they're all the same, then there is a prime to common to all numbers, and by definition, in the same way that we had here, right? So we just kind of assume that means that even we remove one number, while all the remaining numbers still has the same prime, right? So now we can make the assumption that no prime is common to all numbers. And then that means that at least, you kind of dot this out. That means that at least one number doesn't have this 2, right? And if one number doesn't have these 2, well, it doesn't have to be 2, but let's just say one number doesn't have the 2, right? If one number doesn't have the 2, it means that there's a way. So maybe, we have A3 is equal to just the rest of it, right? That means that there's always a way to include this number in a pigeonhole kind of way. I'm trying to fix the scrolling. Oh, whatever. Always include. Oh, fine. There's always a way to have this number such that, in this case, there are 2, right? So you can take a prime, take these 2, right? And there's always a way to add numbers such that the pigeonhole principle holds, meaning that you will get a GCD of 1, right? And from this, you can, I guess maybe another way to think about this it's pigeonhole principle, but also maybe some sort of like linear independence, right? If you're into that. If you're into linear algebra, maybe you'll get maybe that's a easier visualization, right? Is that you'll if you kind of look at these instead of multiplication, you think about these as vectors. You'll find one in which all the GCD is equal to 1, right? Because because you can always find okay, maybe another way to phrase it, now that I think about it a little bit more, my apologies for not being polished on this, is that for every prime, you can find 15 primes in that you find one number without one of the prime, another number without a second prime. So that means that you could always find a number. Okay, maybe that's the other way of phrasing it, is a little bit cleaner, right? So you can always find a number without 2 as a prime, always find a number without 3 as a prime, right? And always find a number without 5 as a prime, and then ... right? And that's kind of the idea. And of course, but one number that has that number, right? So so that's kind of the idea. And once you do that, then now this just becomes an if statement. I'll give you a little bit of a sneak preview of, I guess I did it to 15. I just have an if statement, and then else what happens? Well, else n is less than 20 elements. And if n is less than 20 elements, we can just brute force, right? And that's basically the idea, is that we break it down this way. We can brute force, and just to be clear, this means brute force trying removing one element and see if the rest GCD is 1, right? So that's kind of the idea. That's basically the problem. And just to be clear, I missed this part, right? Totally did. But the rest I was able to get. So hopefully this kind of like, explains the kind of problem that you're having. And it's a very tough problem. I didn't solve this during the contest, during live time, right? So So for me, like I said, you can also do a GCD segment tree. But for me as a result, I do what's it called? Smallest prime factor SIF, right? it's a prime sieve. So definitely look it up if you haven't done it. I mean, this video is already half an hour. I'm not gonna go over it, right? Sorry, friends. But yeah, and yeah. So we separate them out from what I call good and no good, and we keep track of the number of good things, right? As well. We have a helper function get primes that basically decompose the primes from here. Key note is that I actually use a set, right? Because we don't care about duplicates. So just a minor call out, then minor call out from how it's different from it might be normally, right? This is the frequency table that we talked about with the set, so that we could keep track of what indexes we care about. Maybe that's not actually necessary, but I had it just in case for certain reasons. Maybe it'll be faster, but it's fast enough. I mean, timing was not the issue. The correctness was. So anyway, sorted list, which is frequency. List of the frequency. Oh, one more thing that I had was that I don't know if this is necessary now to think about it, but I had a same the number of numbers that are the same, right? Because the reason why I had this here, I think, and I don't know if you need it, maybe you could clean this up, is that if you have a number that's exactly p, you only need one number, right? So you don't need to kind of cross-reference number. I think the way that I implemented, I don't handle one very well, so that's why I have to do it. But I just keep it count. And if one of the entire array is same, then it is just true, right? Because you could just take one number and that number will give you, well, a GCD that is exactly a target. And good count is, keeping track of the numbers that are divisible by p. And here, this is the pre-processing, right? We have the same, we have the good, if it's good, oh, we also divide it by p, so yeah, here. So this is, so we also have a good Boolean array to keep track of what's good or no, it's not. I don't know if this part is super necessary, honestly, but yeah. Otherwise, we get the primes in a set, and for each of these primes, we update the frequency table. We update the frequency table and the sorted list of the frequencies. This is the brute force part we'll go over later. But otherwise, then now we go over count for each query, I and we remove I. And this is just bookkeeping, right? Maybe we could have used the helper for this, honestly. But yeah, we set it to false just by default. Oh yeah, because it's already good. So then we subtract good count. Otherwise, we update, we get the primes. Maybe we can cache this actually, but yeah, for each of those primes, we remove it, right? We do a removal from the sorted frequency list and the frequency table. And then we add I. Well, if it's not divisible by p, we actually don't care. It doesn't change the result. We'll just never pick it. But if it is, then we set good is equal to true. We update count. We update the actually, I guess we have to update this, huh? Did I mess up? I guess we don't really care what the value is, but we should still update this to v. Huh? Do I update this to v? I don't update this to v. That's actually kind of funny. But because if good sub I is false, we don't actually care about what's in there, so that's why it's still true when it's updated. But it's a little bit wonky now that I notice this. But anyway, we set the update. If it's equal to 1, that means that it's p beforehand, right? So we update same. Otherwise, update primes, frequency table, and the sorted list. And then this is the big if statement, right? So if one number is the same, update the count. If we have at least one prime for some reason, if the good count is not n, meaning that if we already do not use all the elements, and the most common element, this is the biggest element on the sorted list on the frequency, right, is less than the number of good count. So that means that the GCD is 1, then we update count as well, right? And then this is the tricky part, that this is the entire thing that I didn't get and took me an hour, right? Is if the good count is n, and I wrote this in a wonky way, but whatever. If the good count is n, that means that all the numbers are used. But of course, we check if even though we used all the numbers, we check if all the numbers are the GCD of all the numbers is 1 or not. Because if it's not 1, then it doesn't matter. You remove one number, it's not going to be 1 anyway. But if it is equal to 1, then we check, we can get 1 by removing a number. Again, this is the pigeonhole based on prime that we talked about. You could reduce this to probably like 7 or something even. But otherwise, with brute force, and the brute force is pretty straightforward. Actually, I did the prefix suffix GCD, and then we just kind of, if the suffix is 1 or the prefix is 1, we return true. Otherwise, we just take the GCD of the prefix and the suffix. So this removes I from the GCD, and we just take the left and the right? So this is the prefix suffix idea, and the GCD of that is equal to 1, then we return true. Otherwise, we return false. So this is actually off, and it's a little bit actually smaller than the brute force bit, so I lied a little bit, but that's basically the idea. And that's it. A lot of talking, 35 minutes worth of talking. That's all I have for this one. I'll show you the code one more time, and maybe even the notes, because why not? So here are my notes. All right. And here's the small prime factor CIF. I write this by heart, by the way, so in case you're wondering. The pre-processing, the get primes function, the processing again, and maybe you could combine these two, by the way, but I didn't. And then this is the brute force way of counting GCD, removing one element. Can we remove one element from the N array, or N15, I guess, and get GCD of 1, right? And then here, that's why I always break it down to removal and add, right? Pretty straightforward, hopefully, with all the primes. And then this is the final GCD check. And that's it. That's all I have for this one. Let me know what you think. Thanks for watching. And yeah, and also, by the way, if you use a GCD tree, which you have to write, well, I guess you could always have a copy and paste or cheat, but then then a lot of this is easier. But I don't know. I think it's about the same. You ask me in difficulty, but but that's it. That's all I have for this one. Let me know what you think. Thanks for watching, and you could watch me attempt to solve this during the contest now. I guess almost, right? And then now we have a 7-pointer, so that means I'm not going to early lunch, but we're up to 526. That's kind of nice. Q4 good subsequence queries. Okay, so we have N and a P. Non-empty subsequence is called good if its length is less than N. Strictly less than N, so not full. The GCD of its elements are exactly P. Okay, it's a subsequence, Larry, not a whatever. So, but the positions matter. I was immediately looking to sort it, but this is clearly not. Okay, so there are more than this. You can also give a 2D array of queries, index, update num sub index to value. Determine but any good subsequence. Return the number of queries for which. Okay, so we return the number of queries, but we only have to determine whether any of them exist, right? So what does GCD mean? My back and neck is still a little painful. I need to see a doctor maybe, but okay, so we have this. So we want, how do I process this? So we have to do some processing and an update and stuff like this, but how do I process it for GCD? I guess I don't know how. Initially, right? The numbers are small, so we probably have to do a SIF type thing. That's fine, that's easy. At least that's been done. Okay, so here we have this. Does it exist? Oh, and P is a constant actually, so we could do it in terms of that. What does it mean when the GCD is at exactly P? It means that you could have at least, you could just have also have one number, right? Strictly less than n. Does it always have to have one number being? No, I mean, because no, because you could have like, I don't know, 6 and 8. The GCD is 2, but 2 does not exist, right? Okay. So then how do you calculate this, right? So this is going, if we have something like this, you have 2 times 3. I mean, it probably has to be something like this, but I don't know, right? Okay, let's do this manually. I think maybe that'll give me insights for Q1, right? So okay, so then we have 4, right? So we pre-process this, we would have 2 to the 2, 8 is 2 to the 3rd, 12 is 4 times 3, right? 16 is 2 to the 4th, right? So a lot of powers of 2s for some reason. And then the GCD. So this would be just not true, right? Because any 2 GCD would be 2 to the 2. How do we process this? Right. And then once we convert to 3, then now it's just the same except for we have 3, right? And then when we update 2 to 6, index 2 to 6, 6 is going to be just this. And then now these two are, wait, what? So the intersection, and n is a big number, but the intersection of number, how do I even process this? Do I not care about the 3? I guess you just care about, no, you do care about the 3, because for example, if we convert the 8 to, I don't know, times 3 again, or you even just convert it to 6, right? We convert to 6, then now this no longer holds. So it has to be this, some sort of weird intersection, right? So I have to have an idea, and I don't really have any right now. Though actually I lied, because the 16 matches, right? So they're like funky stuff like this, but it's subsequence, right? So it could be more numbers, and more numbers gives you finer control. So actually they said that 8 and 6 is good, but actually even if this was 8, these 3 also is good, right? So then now we want to maintain, because I thought we could, I thought maybe we would want to maintain minimal sets, but maybe that's not true. Maybe we want to actually maintain maximal sets, right? But then you have to figure out how to have them first. And what does update mean? Okay, so let's say we have P. Is P always a prime? No, just an integer. I mean, well, first we'll have to, take it out of each number. Okay, so let's say we take it out of each number, right? And so this is no, right? So this is equal to 2 times 2 times 3, so 2 times 6 maybe. It's fine. This is just 2 times 3, and then this is 2 times 2 to the 3rd, right? So 8, whatever. Okay, right? So we pre-process these, and then now, well, the no, we don't care about the no's, right? Yeah, we don't care about the no's because you cannot have them in there because it just doesn't have it. So then, and we might also care about P is equal to 1, maybe. maybe we have to think about it. But I'll just write out the P. I think it's just like everything is true. So, but I don't want to think about it yet. Okay, so the update divided by that number, we have these things, right? So then now, the thing is that we want the GCD of these some subset such that, and is it always the maximal set? I guess so, right? Because adding more numbers can only make the GCD 1. Right? Because as you add more number, you cannot make, yeah, and because we already factored out the number, so I guess that's it, right? Maybe, I don't know if that's quite right, but at least that's good enough for me to give it a pass and get a wrong answer and then learn from it, hopefully, right? Okay, right, so pre-process, right? So here we have, okay, so maybe good is equal to force times n, right? Now for in range of n, num sub I, if this mod p is equal to 0, then good is equal to true, and then num sub I we could just divide it by p, right? Yeah, okay, we'll do this for now, and then otherwise good is equal to force, right? Okay, and then it's just keeping track of states, right? And then now, yeah, we do another pass, right? G is equal to, I want to say 1, but that's not quite right, right? What do I want it to be? The default, so maybe I'll just say none. It's a little bit yucky, but it's fine. Why is this giving me issues with auto indenting? I don't know. Am I missing a? Oh, I forgot in. Okay, I mean it was legit. Okay, so if good sub I, then G is if G is none, then G is equal to num sub I. Else, then G is equal to GCD num sub I G, right? Okay, I mean this is fine, but I think I have to be a little bit smarter than that for the updates, because we cannot recalculate this every time, right? And adding numbers is easy, but removing numbers means that we have to be a little bit smarter about the GCD, right? How do we keep track of the GCD? Maybe that is the hard part. I mean, or at least I don't know that part. But I think, otherwise I think this is right, and this is finished if I could figure out how to keep GCD updated, right? Or we could add numbers and subtract numbers. Okay, right. So then GCD, what is the contribution? Because when you remove a number, you could have a bigger GCD, and we have to be able to handle removing a number. How do you remove a number? Maybe I don't know that one. Because here we remove this one, say, right? Like we just do it to another prime, right? And now we have to remove it. So instead of 6 times, well, GCD of 6, 3, and 8, we have to go to GCD of 6 and 8, right? Okay, or maybe the other way is more interesting, is if it goes from 1, let's say, I guess this is 1 actually. So we go from, okay, so then now, what does that mean, right? We have 1, 2, we have to be able to recalculate all the GCD . Well, okay. I was going to say, well, we know the order in which we do the queries, so maybe we could pre-process the queries in a way such that we do them in like reverse order or something like this. But that seems like crazy talk. Like I really need like a log n way of doing it, right? Okay, right. Yeah. Otherwise, we have 4. All right. Maybe I'll just write this out first. What do they call it? I and we. Then now we update I to we, and then fetch, which includes fetch GCD is 1 count increment return count, right? But okay, so that didn't really help because the update part is still the tricky part. Okay, because adding numbers is easy. Is changing numbers easy? No, changing numbers is just add and remove, but the remove part is the hard part. Okay, so how do I remove a number from consideration, right? So okay, oops. All right, we don't need this now. I think I have the idea for this part. Maybe I'm wrong. Okay, so now this is the problem. We have GCD of 2 times 3, 3, and 2 to the 4th. And then now the GCD is 1. Is there another way of saying it's 1? I mean, you can look at the primes, right? But we just have to know that it's non-1, and the intersection of 2 things is because then now we're moving. So then, like, do we have f of 2 is? I see. So then now, for each of the primes, we have a set, right? Maybe? I don't know how to deal with like, well, they just have to be 0 or 1. So primes, if we have multiple primes, it doesn't actually matter as long as all of them has at least one of the primes, right? Like we don't care whether it's the common factor is 2 or 4, right? We just care that it has at least 1, 2. So then now maybe we could keep track of set of the indexes, right? Okay, that could be something. And then for each key, it has to have all of them to not have thing. Okay. Okay. That means we have to okay, now it's time for Sif, I think, right? What's it again? 5 times. Whatever. Right. I forget what SPF stands for. Did I just write it? Whatever. Smallest prime factor? Oh, okay. Thanks, Larry. Okay, right. So then now, we also do this P is equal to 1 first, and length of queries, right? Because it always. Oh, is it length of queries or 0? Actually, that's not true, right? Okay, do stuff. That's because, yeah. Actually, maybe it's just maybe I don't have. Maybe that's not a special case. Because then now maybe everything is good here, right? Yeah, I guess so. Because yeah, I guess they shouldn't have to change. But okay, but we still have to do this part. Okay. Is equal to 2. What? If SPF of I is equal to I, then it is prime, right? So J is equal to I. Actually, I actually don't remember this part. Oh, it's a little bit rusty. Whether it matters, it is okay, right? And then now I remember, right? Okay, right? So P we don't care, and everything is just 1. And then now, what did I say we were? Okay, so we don't do this anymore. Maybe if this is good, then we have to yeah, maybe have a counter, right? It's a counter for each. No. One default dict of list. No, set, right? So then now we want for each prime. So then we have num sub I. That's already updated. We want the prime factors, right? So yeah, maybe I just have a helper, right? Right, and then for I don't want to use P because I feel like I'm just confusing it. But for prime in PS, let's go with primes. For prime in PS, f of prime dot add I, right, for the index, right? So then now what happens? This should be a set, right? I mean, we can make it a set. Let's make it a set. Let's write that first then. Well, x is 1. This. Primes dot add sp SPF of x SPF of x, right? So that's basically it. And then now right? So then now if f of prime is equal to all the numbers in the thing, right? All the numbers that we care about. Wait, no. How do I write? How do I think about this? So the GCD is. Maybe I'll write it afterwards. Okay. So the GCD is 1. Okay. So GCD is not 1 if one of the keys is. If one of the keys is all the numbers that are in it, right? And we cannot do any better. So okay. So good count is equal to 0, maybe, I don't know. Okay, and then now we can write if. I see. I really need to keep track of that too, right? How many numbers are so then we could keep track of it. No. We can just write. I mean, we could instead of keeping track of it, we can have ff for full is equal to elections.default dict set, right? So then okay, right? So then now we have for key in f.keys, which are all primes. If length of f of key is equal to good count, then ff of ff we want to add no ff of k. No, is it just set? What am I doing? Yeah, okay. ff we want to add k, right? And then that's it. Okay. And so if length of ff is greater than 0, that means that 1, then it is not a GCD is not 1, right? Yeah. So okay, so if this is the case, then count increment by 1. So we can put this here. And we already had done this. Now we just have to do the update. Update. What am I doing with the update? So we remove I, add I. I mean, add part is maybe simple. But we'll do the remove first, right? So what's the previous number? If good sub I, oh, okay. Is that easy to do first? If it's already good, then, well, set I is false, but what are we doing? Primes is equal to get primes sub num sub I. And for each of those prime, for prime and primes, f of prime dot remove I, right? So we remove that. But then now we go if length of f of prime is equal to 0, then we delete the key, that's fine. But we also want to do ff dot remove prime, right? Okay, so that's the remove if it's good. If it's bad, then we just don't care. I mean, we care, but none of this needs to happen, right? And then now we add I, right? Add I, okay. So if v mod p is equal to 0, then that's where we care about. Otherwise, we just skip, or we don't care because it doesn't change the answer, right? So then good sub I is equal to true. Primes is equal to get primes of v. No. Well, yeah. Well, let's do num sub I is equal to v divided by p, similar to what we have there here. And then now we have to do the get primes thing, right? Because I kind of spread them out for some reason, but anyway, for prime and primes, f of prime dot add I, right? And yeah, if length of f of, this is wrong actually. It just has to be not equal to good count, and we have to keep track of good count. Okay, so if this is equal to good count, ff dot add prime, right? So that's done, but this part is not right. If it is less than good count, good count subtract 1, good count add 1, right? But something feels a little bit off. It doesn't. I have to. Okay, let's run it real quick. But all right, at least. All right. Well, at least something's weird in a good way. Okay. So k is prime, right? So for the primes, with the length of it is equal to good count, then yeah. Otherwise, when we remove, I mean, this is always going to be less than good count, but what I want is before the removal, if it's good count, and also then we don't do this. That's just, all right. So if it's equal to good count, and also we remove it, I think this is a little bit more right. It's a little bit more right, but still not right, I suppose. Okay. I think the idea is better. I think this part is just never right because we need to do it beforehand. Yeah, okay. But now it's removing things, right? Where's the invariant? Oh, this doesn't get added, so this has to be added. No, this is fine. So if all of them has it, then yeah. And this wouldn't really add anything, I think, because it would just keep doing it. It's on the removal. The removal, well, you could actually, and on removal, you can add a prime. That's the thing, right? So on primes, we want to remove one, but on these, Well, so this is before we remove, right? Oh, this is hard, isn't it? It's not just this. It's that. I mean, it's not that hard. We can handle it. But it's just that on removing, actually some numbers can get back into here, which is why maybe there's some like weird interactions here. So we have to just do another level. This is so annoying. I mean, it's 42 minutes left. I mean, I think we should be able to do it, but it's just, like I said, very annoying. Actually, maybe we don't even need FF. I think we have just maybe SL is a sorted list. Maybe that's a little bit cleaner. We don't care about the actual primes anyway. Though maybe it helps with debugging. But what we care about is for every prime we add, then now, what does that mean? We just want to keep track of the frequencies here, right? So SL of, we remove length of f of prime if it exists, which it should unless it's 0, right? And then we add length of this, right? So then now SL just contains a solid list of all the frequencies, and yeah, and then now this is a little bit cleaner to write, right? Because then now you can write this. And it doesn't matter which one you remove anyway, so it just has to exist. Maybe I'm wrong on that one actually, but okay. So you have something like this, right? So then now it's not the length of LM, it is the, so the maximum element, if this is equal to good count, then well, if it's less than good count, more specifically, right? I don't know. I don't know. This should not come into play, but I could be wrong. I was wrong with this. Oh, yeah. I guess zeros are never added. No, I mean zeros could be added here, but maybe not. Okay, still no bueno, but I think I feel a little bit better about this. Let's see, right? So we have 1 and 3, which is not very helpful, honestly. But okay, let's see, right? So primes, right? So F we have 2 and 3. So 2 is so we divide it by 2, right? So after the 2, then these 3, and the 3 has a 2. Okay, right? So the sorted list is 1 and 3, 1 element and 3 elements, right? And then now, wait, what was the first operation? Oh, 3. So that's why it doesn't change anything. Actually, no. Well, it does. It should change stuff. So we should maybe do it beforehand, just for visualization. Okay. Right. Okay. So this is what I expected. Okay, that's good. Yeah. Okay. And then after one move is this. The sorted list is 1 and 3, which is correct. Right. No subsequence, because yeah, this, right? Yes, subsequence 8 and 6. Update 2 to 3. Now we removed this one, right? Isn't that the part of it? Or just the 2 rather? Did we not take the re correctly? We might not have, Yeah, okay. Because this should be num sub I. And so we did not remove the P. Okay, so 1, 2, 0. Okay. I think we're in a good place. We might still have silly mistakes, but at least this is enough for me to YOLO submit. Let me remove some debugging stuff, right? Because at least on the cursory, I didn't really look too detailed, but it looks okay. Okay, 0 and 7. I don't know that I handle 0, so that may be. Oh no. 1 and so this we converted to 7. I mean, we got pretty far for an edge case, so what does that look like? I mean, it's because now it has a 1 inside, but I don't know what it means, so I guess we will see. We will see better if we use the test case though. Okay, so so there's some like weird things with 1. How do I handle it? There's a weird case with 1 because my prime doesn't add a 1, right? So that's why it doesn't like factor that in or whatever. Does this only happen when one number is just by itself good? Okay, so this is true. If this is 1, right? How do I write this? If num sub I is equal to 1, then it's just true by default. But how do I write this in a coherent way for the future as well? Right. I mean, how do I want to write this? Because this only happens when there's one element, and it, well, I mean, that could be have multiple elements, but multiple same one item elements, but you only really need one because you only select one, right? So yeah, maybe we just have I don't know. I don't like the way I'm writing this, but maybe that's good enough. We'll see. Right, so maybe same is equal to 0, right? If it's good, and that has to be good, right? So yeah, if num sub I is equal to 1, because we already divided this, then same count is equal to right? All right. And then now this is remove, right? So it's good, and something like this, right? I don't know. Maybe I could have thought about that earlier. I mean, I don't know. I'm not happy with that solution though. I mean, you probably could write it cleaner way. And now I have other ones. P is equal to 1. Oh, this is, I mean, it's further along, so it's a new case. I'm not surprised that I have so many edge cases, but okay. It's still a little bit sad though. I mean, I don't know. The P is equal to 1, maybe it's a little bit more obvious. This one I'm not sure yet. We'll have to analyze. We have 33 minutes left, so I'm not, I guess we'll have to see. P is equal to 1 may be a case though. Okay, so here we expect 0, right? Divided by 1. Oh, the GCD is 1. So currently we select the 0 to 4. There should be, is this not a, isn't this GCD 1? I'm so confused. Why is expected 0? And then 1 to 6. I mean, this is definitely not, but isn't 4 and 3 just 1? Or am I confused? Oh, am I solving the wrong problem this entire time? That would be funny. Non-empty. Oh, we cannot have all of them. Why? Why would you do that? Why would you do that? Why wouldn't you just like, be able to take all the numbers? This is annoying. Okay, well, I mean that's not even I'm curious why they make you do that. But okay. So I did miss this because for some reason that's the case. But how do I handle this? I mean, it's just another part of this if statement, I think, but an annoying part. But good count. How do I handle this? Okay, so the good count for this one is going to be 2, right? This is 2, this is 1. I guess this has to be NSL. Wait, is this right? Right? No, well, it's basically this number is going to be just 1. Why am I guessing? Let's print this out real quick. Did I use this? Okay. Why is my button gone? Okay, so you have 2. Right? Okay, so you have sorted this of 1 and 1. Maybe we should remove the zeros, but whatever. And this is the state in which this gives me a 1, I think, right? It's because 1 is less than good count, right? Why is this the case? I don't know how to do it. Okay, because what does that 1 mean? That 1 doesn't mean, it means that only one number is thing, but that means that, why is this so annoying? I actually don't know. I mean, that minor twinkle is actually pretty big, because I can't just check for it, right? Okay, that means that one number has this thing, but that means that because multiple things can have n-1 components, and then in composite they might have a GCD, right, of 1, right? Is this a case for n is equal to 2, or am I just tripping? Uh-oh, my disk space is getting low. It's okay, it's a couple of gigs. I just have to make this video short somehow by finishing it. 28 minutes. That is wild. I am deleting some things for space purposes. Hang on. I also don't know. I don't think you can just check for that, right? But okay, so what if you have 223? 223 is still the same thing, right? You convert it to 4, convert it to 4, 443. No, 443 is fine because then no. Maybe it's an n is equal to 2 thing. I actually don't know. I mean, this is not good enough. Basically, you want the existence of a num. No, because the idea here is that if they all the numbers share. Okay, if all the numbers share a component, then it's no good, right? Okay, that's fine. If all the components minus one element, how do you check that it doesn't have all the elements? How do you check? Okay, well, I have to go back from first principles. I thought I was done, to be honest. The observations did not take this into account, so I'm like a little bit off. Wow, you are so annoying. So okay, so you have so they all have one element. So this is not possible. So if it's n, right? Okay, so okay. First of all, it's okay. Maybe I can define that. I don't know. Good count is equal to n. If this is the case, then that means that we have to remove one of the elements, right? Okay, so if it's equal to n, then we have to remove one element, but that element may change the result. So we have to. Okay, one is that. Yeah. Okay. Let's do this here first. I feel like okay, and then now if it's I mean this isn't even quite right, but I just want to get this logic right? Okay, so this is true. Right, okay. Now, if this is equal to n, I don't know if this is quite right, but I'm going to YOLO it because I have no idea now, to be honest. I need a. Yeah. Is this even right? I don't know. It fixed this one. I forgot all the other ones. So we're gonna. Well, let's at least take a look at the examples. 1, 2, 0. Okay, YOLO submit. I don't know if this is enough, but yeah. I mean, I'm not surprised that this is wrong now. That last bit, wow, really got me. I didn't think that was going to be a big problem. Huh. So you have 2. Yeah, so what is this? You have 2, 7, 2, right? Set 1 to 12. Why do they do this? I guess to make it harder, but is it harder for other people or just like my technique? Huh. Okay, so we convert this to 12, so that means that this is a 6 now, and then now this is 0, right? So why is that wrong? Or like, why am I giving a 1? Right. So the list, you have a 1 and a 3. Good count's n, okay. One of them is a 1. Maybe I don't know, because it's now choosing just this one, but that's not good enough. I mean, that's what I suspected, but wow, that's so annoying. Because yeah, after one change, all of them are divisible by 2, but you have 3 2s and 1 3. 1 3 does not fix it, right? So no. Maybe I just have to do this. I don't know. Now I'm just like guessing, honestly, which is not great. Because if it has good count, if good count with all of them are things, I don't think this is right. But gonna have to give a 3 wrong answer to see what yeah, this is what I would expect. But wow, that one change, maybe it's just p is equal to 1. I don't know. Because my cases are from p is equal to 1. Can I handle it with p is equal to 1? No, I mean, p, that shouldn't matter because you just change p, you can multiply everything, right? So it doesn't matter. But here, all right, let's print this so I don't have to figure it out. Now I don't know if I could solve it. I put 0, okay, good count is equal to n. So we have to have a logic there. Okay, right, so ourselves greater than 0 and good count is equal to n. If good count is equal to n, then when would you be able to? So like you want like the intersection of these two sets or something like this, or intersection of some sets. Man, why do you hate me? Wow, that one thing, huh? Because then now instead of counts, we need like set intersections or something, right? Because now the 0s and the 3s and the 2s, wow. Okay, so the good count is equal to n. What is this case that I was wrong on? Maybe I'm solving it incorrectly for here. Maybe this is like just weird. Though maybe I can't solve this anymore. Wow, that is annoying. It is this case, right? Okay, so this is those three. So this is the only odd case out, and it is basically we added a count. We added a count when it shouldn't have been, and it should not have been because we use all the numbers. So the good count. I see. Maybe we could do something like this. I don't know if this is quite right. That's not even right anyway, but so this is the thing, because it is saying that, I mean, this is exactly the same as this, so I'm not surprised. I'm trying to figure out how to articulate this, right? So the biggest number maybe it's just as simple as this. I don't honestly, this is see what sticks, just because I have no idea. I don't think it would work because it's just so wonky. Wow, I guess I just have no idea anymore. This not doing the entire thing is ruining me. I honestly did not consider this case, and I don't know how to handle it in 15 minutes. Okay, so then we have just 9, 5, 13, right? So that's good. And then now we convert this to a 10. Oh no, whoops, 10, 5, right? Now this is no good. All right, what is the thing about this? So there's 1, 1, 2. All of them are going to be 3. So this doesn't even come into play, I don't think. Good count is not 3. Wait, so why is this wrong? Well, how am I getting this wrong? Good count. Oh, good count is always 3 because p is equal to 1. Okay, fine. So you have this, and then now the biggest number is 2. So if you remove one number, then this is no longer true. But you just remove another number, right? So I think it only happens when n is equal to 2. Maybe, right? Right, and then I don't know if this is right, but anyway, 3 if right, and then now do we always have 2 elements, or can we have 1 element? Always 2 elements. What happens when we have 2? When we have 2 elements, then now we can maybe just num sub 0, right? So here, if well, it's more nuanced than that, but because I have a good flag. Okay, a good count. Else we just do the same logic. I think maybe that's fine. I don't want to think about it too much. Okay, so if the good count is 2, then now if num sub 0 is okay, or if they're both good, then now one has to be in nums, then something like this. Maybe n equal to 2 is just a weird case. I'm hoping so, because otherwise I don't know how to solve it. Because I think with 3 elements or more, you just kind of YOLO, right? You just could remove one. I'm really hoping. Oh no! I mean, we're getting closer, but I guess not. Okay, so we expect 0, but we're getting 1. But this should not have anything to do with, because we have n is equal to 3 elements. So what is the change here? I mean, we add and remove the same number, right? So what are the state changes that made it not true, right? So it's all 5. 1, 2, 3, 4, 5. So yeah, so why? So good count. Because you need all 6. No, it's just that. Huh? What is the? I mean, this looks exactly the same. So why am I getting output is 1? So no prime is on all of the numbers, right? But is it like some weird summation? Maybe my idea is just really wrong, and that's kind of the whole thing. Why is this wrong though? Well, rather, why is this not? What is the LCD of this? Is it not 1? I guess maybe that's 1, but list object cannot be. I thought you could do it this way. You know, the GCD of all these numbers are 1, but you cannot remove any of them. I see. I mean, okay. So it's not just an n equals to 2 thing. I'm just fundamentally doing this wrong because I had an assumption about all the numbers. Well, I just didn't think that that would be a big part of it, to be honest. How do I handle this then? Basically, these are all 5. You need all 6 to do it. Maybe something like this. I don't know. Would this really fix everything? No, this already fixed this. I'm just wondering if you could have done like the smallest amount. Or maybe that doesn't even make sense. I mean, this still doesn't fix this anyway. But huh? I thought I had it, and I think our ideas were pretty in line with the difficulty. But I think the strictly less than n part is wild. Huh. Now we only have 7 minutes. That is sad. I really thought I had it. I'm missing some logic. I mean, I don't know. I think my problem is that I'm trying to like hack things into this, and it may require a fundamental rethinking, and I don't know that I have time for that. Right? That's the biggest issue for now. It's just that, yeah. I mean, I see why it's wrong, but there exists a plan, but that doesn't even make sense. I mean, the thing that I had before doesn't really make sense, because then it means that, I mean, this set of thing can appear. No, that doesn't. Well, yeah. I mean, this one doesn't really make sense anyway. But I was thinking of like, okay, well, if a number appears only once, that doesn't mean. Oh, there exists a number where the GCD is 2, maybe? Because 2 then, well, one number has to be the same, but if you have 2 numbers, then what happens, right? Let's get rid of this for now. Maybe just the same idea though. Okay, so that means that either this or a number that exists that is 2. So maybe bisect left. A number that exists that is not all of them, right? And no, that doesn't make sense either, because that set of numbers can literally by the opposite of the things that I'm doing, right? So here our count could be 1 1 1 1 1, because that's the emptiness, right? So then now a number that exists that is less than n minus 2. Something like this. Right, so this is fine. Otherwise, then now, if good count is equal to n, it's greater than 0, something like that. I mean, I have no time, so I'm going to have to YOLO it anyway. I have 3 minutes left in case you're wondering. It may just be wrong. I didn't even check all these other ones. But yeah, I mean, this one we had before. I actually, technically speaking, I removed that one because, I don't know, because we don't have enough test cases. But okay, so I write 0, but there should be 1. Because we remove 10 and then just 10 and 9. There's 1, 1, 2, right? So n minus 2. Is it bisect, right? Did I mess up? YOLO, because like I said, I only have 2 minutes. That's why. Did I mess up on the bisect? Okay, well, doesn't matter. I mean, this is one of the ones that I guess maybe this one should be in C1, I think, but I just have no idea. And I think at this point, I think the biggest issue is that I don't know that it is a fundamentally like, is it something that I can fix easily, or is it that I just fundamentally got the wrong idea on how to solve this based on that miss? Like, I thought it was a small piece. It is clearly not. So, yeah, I mean, you know, sometimes it's just as easy as, well, not easy, but sometimes that is the difference, right? Because this piece has 1 and 3, but this one is, yeah, this one just means that by itself is a 3. So that is not good enough. We need a 0. No. What do we need? We need a 2. I think that, so we need at least 2 numbers. That's what I said before, right? Okay. Maybe something like this, right? Index equal. Okay, bisect right of 1. If they exist, then we're good, right? Something like that, maybe. I have 30 seconds, so I don't really have time to. I mean, this is just way wrong anyway. But I have 4 seconds. I'm out, but I just want. I think this is actually maybe fine. Nope. That'd be fun if this works. I'm printing stuff too. Maybe. Oh no, this is expected. I see. So we already got this one wrong. Okay. I mean, at that point I was just, you know, testing anything. But I want to see why though. Is it n-1 or n-2? Maybe it's n-2. Nope, still very much wrong on case 7. Case 7 is this one. Why is this wrong? One, 1, 2. So it exists the number 2, where n-3 is bisect left of. So now, well, I'll put 0, but there should be 1. I see. So that's because after you convert this to a 10, then now 9 and 10, right? So 9 and 10 is 0 and 1 index. It's the intersection of this and this. I think that's why. But I don't know how to do it. When people did it in 10 minutes, Not your usual suspect though, so probably some help involved. I just don't know how to do the where are the smart people? Don't see any smart people though. Don't see anyone I recognize. I refuse. Did I miss something obvious? I do wonder. I mean, I still haven't clicked on anything yet, but let's see. All right, let's see. Segment tree. I thought about. I mean, I did think about segment tree, but I thought that by the time I finished it, I thought I had no time to do it with segment tree. Yeah, this is what I had. What is the segment tree on? The GCD of the thing. Right. All right. What is this? N is equal to 2. Okay, so we build a segment tree based on what? GCD of the subtree. Okay, what does the update do? Yeah, I guess this is what I was working on as well. But what does the update do? So this is the entire thing, right? Maybe I'm not understanding. What is the count? So, okay, so the count is equal to n, and n is equal to 30, then... Okay, so you have to check nums. I mean, this is, I mean, with, I mean, I know that they did with a binary index, or sorry, segment tree, but this is very much the same as what we did, but maybe that's it. Our sliding window, removing one element. I'm curious why that, maybe that is the idea, just brute force. If it is 30, then you have pigeonhole, I suppose. That's the idea. And if it's not, then so we could play around with that. Yeah, otherwise you just tick all the LCD of all the numbers, right? I guess it's just pigeonhole, but maybe, I mean, maybe that's the insight I missed, but that's like, I don't know, way weird, but yeah. Otherwise, if good, if, I don't know, let's go F good. And I'll probably just, this is just cheating at this point. It's just yeah. Well, this is for all, that means that all the numbers are good, right? So we don't have to do a pre-processing step. But I'll just do what they did with prefix, suffix, right? Just kind of annoying. right? And then now we have so 1 is the first number, right? So to skip this one, well, it is just else GCD of I minus 1. Something like this, right? Of course, GCD of 1. No, it's yeah, no, this is right. Is it the last one or last two? Yeah, I think it's the last two. So this may be a little bit, this may get out of bounds. We should have at least 2 elements, right? So it should be fine. Look that. That's kind of the idea that there was a. Maybe I just missed the pigeonhole part. I mean, this is really light, but maybe I missed the pigeonhole. I mean, I kind of did the lazy pigeonhole, so maybe I'm wrong here. I just kind of copied what they did, to be honest. So maybe there's some additional logic needed. I just kind of copied this logic. But you can see that if this is all 2, then yeah. Wait, why is this? Oh, if okay, so if they're all filled, if it's less than n, then it's not. Huh? How do I write that? Well, how did they handle it? They get the GCD of the entire thing. I mean, they just get the GCD of the entire thing, right? So if n is equal to 30, why is that? Why does that work for them? Count is equal to n. Do they do anything funky beforehand? Maybe they do. They walk the GCD tree. I mean, I don't know that they do anything quick. I mean, I also haven't looked at the code too tightly, but and if we don't do it, then it just times out, right? So we have to do something like this. I assume there's a lot of queries. I don't remember the constraints. Yeah, I mean, this, I imagine just times out. Then how do they get this part? Am I missing something? Okay. I mean, this part I would have gotten if I, but that's the part that I didn't figure out. There was some picture. Oh, Well, I could write something like length of SL with a unique number of primes, but I don't think that changes anything, right? I mean, there is some pigeonhole stuff, but it just means that this fails, and then now we do this code, right? Which is not good either. I guess this has to be an else, but still. Do the check nums matter? Do they do a set or anything weird? I don't know how they get it though. Maybe I'm just confused. I mean, this is basically all I wrote anyway, but the check for n is less than 30 is fine, but what? How does this work? I'm just going to copy it. Like I don't know, maybe this, because this is like one of the last cases. It could be that it could be that this is just put in afterwards, right? So I don't know. So I want to see real quick whether it's just me or, no, it is. Why? How does this work for? Oh, I didn't put in that case, but it still passed. So clearly, now I lost the case. How does that work? I mean, I do stuff like this as well. It's my all good function or whatever it's called. But so either that or this is just fast enough, which is crazy if true. But no. I mean, I still don't get how. All right, let me get the case again. I mean, it's gonna time out, but that's fine. Or wrong answer because I just do +1 without thinking about it. Oh no, this one would time out because actually I changed it from yeah. Okay, right. How does the C++ code work then? Oh, there's an extra space for some reason. How is this so fast? What? Oh, I forgot that I need semicolons. And noob these days. So it doesn't even go here. Why doesn't it go here? Oh man, I always forget. It's been so long. And also this is printf. Oh. Well, maybe not. How? No, I'm just curious. Okay, so it doesn't call here because it's curious never equal to p. Why? Oh. Wait. Yeah. I see. Because their GCD is well, just not that, right? And the way that I do is by look, my GCD is this stuff. Well, I think this has to be. So my GCD has to be 1 first. Okay, I see. I see. I forgot about that part. I just kind of copy and paste code, I suppose. But does it still time out? It still times out because this part may be true, right? Oh, actually, maybe this is now. What was it? N. I can't even cheat properly. This is why I don't cheat because I don't know how to cheat. You can see that I can't even cheat properly. But okay, let's see. Right. All right. So I guess that's it, huh? So I guess there was a quote unquote easy fix to it, which is this pigeonhole E thing. Why is this good again? Is this true? I'm trying to think through the logic. I mean, this part obviously is fine, but n is equal to 30. What does n is equal to 30 mean? That means that there are at least 30 numbers. If there are 30 numbers, but why can't they just all be the same thing? out because they're not the same thing, because here and then the print, that's where the pigeonhole principle comes in, right? Because they're more than 30 primes or whatever. So as a result, you don't need to do it because I see, because they're more than, okay, that's ridiculous. That's such a hard reduction. I don't know. I mean, hard for me anyway. Let me put a screenshot in. All right. I mean, I guess that's it. That's what I have with this one for now. I've been sitting here for too long, and my back is aching. So yeah. Well, let's do a quick retro, I suppose. Though I don't think, because this ended, it doesn't really give me my things, does it? I don't know. Maybe it does. Maybe it doesn't. Okay. I mean, I had like 90% of this. I just kind of the prime pigeonhole thing is a good one actually. This is actually pretty good. I mean, like it's something that I could have gotten, but I don't know, maybe not realistic. And what I mean is that I could have gotten it in the sense that like it's in my skill set. I know how to do it. I have done something like this in the past, but you know, just didn't do it this particular one. And I wonder, you know, I mean, I know this is cheating, but I just see. What is what? Why is this like a n loop thing? Oh, n is greater than 6. Huh? They did only 6, huh? And then the rest is I don't know what this is. This is like union divide and conquer thing. But now I'm curious. Can I have done this like is this better? Like, was this sufficient? We saw a 6. Huh. I don't know why though. I mean, it's not even a big deal. I mean, 30 we can. Oh, actually, maybe 10 because the numbers are not as big. Then there is like what was it? 2 times 3 times 5 times 7 times 11, right? It's already 2,000. Times 13 is 30,000, and 30,000 is already yeah. So okay, I could see that, because basically pigeonhole based on primes, right? So maybe that's fine, right? So you don't even need to do 30, right? Because even if you're lazy, 5 was it 50,000? 50,000 is I don't know, like 12 or 13 or something, right? So you could even just do something like this and that'll be fine. But I mean, obviously I didn't get it during the contest, but I mean, I got most of it. I just couldn't figure out how to do this one. The pigeonhole was the big thing. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's problem. I don't know what I'm doing with my hands. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.